y'all, what's going on? I'm Olaf, as she just mentioned, and it should be readily apparent by now that I'm here to talk to you today about software-defined storage on multiple architectures. Just a level set up front. This is certainly not a technical deep dive, but what I'm going to be doing is essentially be sharing a use case scenario, namely how we use OpenStack in the Poughkeepsie lab in IBM Storage. In retrospect, choosing software-defined storage as a term to use in my presentation title was perhaps a bit vague. We're clearly not testing the entire concept of software-defined storage, but rather a particular implementation of it. The concept itself has been popularized for at least the past decade or more through following similar trends such as software-defined networks and software-defined data centers. Anyway, and all the while, whoever authored the Wikipedia article on software-defined storage, they may consider the label to simply be a marketing term, but clearly I would position, I would claim that there's a clear difference between the way, say, the file that represents my slide deck is saved on my laptop and how it would be stored in a high performance computing environment, or at least you would hope there would be. One of the more recent and certainly more popular technologies to implement software-defined storage is, of course, Ceph, for which there are at least two other talks at Scale 22 before it's all over, but there are certainly others. I don't know why that's blue because it shows up white. Maybe you can read it. But this is certainly no exhaustive list, but working backwards towards me through time, roughly you have other technologies like Hadoop and Gluster, but working your way all the way back to what is perhaps the granddaddy of them all is the subject of my specific use case. That is because we are using OpenStack to test the storage tech formerly known as GPFS, which stands for General Parallel File System, but these days it's called Storage Scale. I'll be using GPFS and Storage Scale interchangeably throughout this talk. You may even hear me call it Spectrum Scale, which is what it was named up until 2 or 3 years ago. Why the name change, you ask? Well, it's funny. As fate would have it, there's a local company that sued IBM for the rights to use GPFS as an abbreviation, and they won. So that is a complete lie. Although I was just making sure you're paying attention, but this company does exist, and they're right down the road, 8 miles away. You can check them out. I'm sure they have quality products. Anyway, what do we need to virtualize and simulate a GPFS cluster in OpenStack? Well, in revising my talk, I went through and I actually ripped out this diagram in this section because, one, there are more than one way to implement a GPFS cluster. There are quite a few, and to try to handle all that in a talk, what could be its own talk, we can simply suffice it to say that we just need some X number of VMs that are running the GPFS software, and it turns out OpenStack can do that all day long, every day. And number 3, we're not really here to talk about the specifics of Storage Scale. We want to talk about OpenStack. So yes, in addition to these cluster nodes that we need to virtualize to recreate a GPFS cluster, we'll also need some attached storage, which we will simulate with cinder volumes. And then while a GPFS cluster can simply use a base install would use just one network to allow for any combination of install options that a user could come up with, we actually need 3 networks. In addition to the public one, a daemon network and a SES network. And as for that attached storage, we'll need to make sure that every VM in our cluster is attached to every single other volume. Luckily for us, multi-attached cinder volumes have been around since the train release, if memory serves, of OpenStack. So without that, this exercise would be quite an exercise in fruition, or not in fruition, and you know what I'm trying to say. It wouldn't work. So in the Poughkeepsie lab in IBM Storage, the OpenStack environment that was set up was named Frost, and it was set up as a dog food effort. That is to say that they were going to that it uses GPFS as its storage backend. So not only are we going to test GPF cluster storage, we're going to use it on the back end to physically provide those volumes. So this required, up until this point, there was no GPFS driver in the OpenStack project, so one had to be written. It didn't implement all the functionality that most Cinder drivers have. It was some of the backup functionality is failing. IBM, no big deal, because IBM no longer supports the use of this driver in any of their current releases of Spectrum Scale, Storage Scale, whatever it's called. But it still works. As in an exercise last year, I had to prove to a customer who has a legacy support contract that they're still paying for, saying that IBM would support the GPFS driver. I had to prove to them that when they made their upgrade to RoHS P17.1 that it would not break their storage. Anyway, I digress. Excuse me. Back to the Frost environment. So each compute or OpenStack compute host in the environment, they are represented in the middle of that diagram there where it says sample node. Each one of those compute nodes, in addition to running Nova and whatever networking processes that need to happen for that. For a normal OpenStack compute node, it is also running the GPFS cluster software. As a result, so each node has a total of 6 Ethernet connections, two 10 gigabit connections each for the GPFS public and the OpenStack provider networks. You see those represented by what look like to me light blue lines from up here. I don't know what they look like back there. Not pictured are the single Ethernet external network connection, as well as the baseboard management controller for those nodes. Let's not forget, each node also has 2 fiber channel connections that give access to the SAN fabric, where all the storage actually happens. In addition to the complement of OpenStack controller and compute nodes, we set up an infrastructure server, not represented here. We just have to think of it in our minds. So outside of all the OpenStack services, there's a extra node we're calling our infrastructure server. It runs the GUI for said GPFS cluster. And since that GUI is utilizing and taking up that web server, all the Red Hat and SUSE repos that are offered up by the server are using FTP. Also, daily builds of the GPFS software that we're testing are copied over and provided by this FTP server. And the last thing this infrastructure server is doing is hosting our first set of Python scripts that enable user empowerment, and that's dubbed the Stack project. For our case, Stack project is a way of automating all the steps needed for adding a new user, which most of the time in OpenStack is just adding a user. But yes, of course, a new user would need a user account. But in our case, we're providing every user with a project. We're also providing every project with 3 private virtual networks that are not shared. Each user gets their own. The ones that we mentioned earlier would be needed to replicate a GPFS cluster. We're also setting up a virtual router to handle traffic from the external network to what a cluster node would consider its public network. And then finally, we are setting up a VM for each user to use that we call their management host, that they use as their Bastion node. So here is the olaph example. So the little box closest to me between the blue and the orange networks is the router that's handling traffic between the external network, and the green public network. The lowest box is the said management host, where the user's using for Bastion as a Bastion. And then on the right we have, let's see, the top three are cluster nodes that are running GPFS, and then the one guy at the bottom is just hanging out a VM that's not associated with anything. He's probably, I used him to make an image update or something. All right, back to, so back on this management node, this VM, the reason a user would want to log into it as a Bastion is because we've also uploaded our second tool to them, and it is called, we call it the Scale Cluster Tool. It makes heavy use of this guy right here, which is what the cloud team at and Spectrum Scale have published on IBM's public GitHub account, which is called IBM. The name of this particular repo you can read yourself, IBM Spectrum Scale installed infra. So they have written a slew load of Ansible playbooks that go ahead and take care of most all of the steps you would need for setting up a GPFS cluster. Not all of them, because what we do is take all of these Ansible playbooks, we tweak a few of them because we found some errors, add a couple of our own, throw in some more Python in there, and wrap that all up and publish that to the user's management host. Again, most of the legwork for the Spectrum Scale cluster is done by these guys. Gotta make sure I give them credit where it's due. So when a user logs into their management host and calls this Scale Cluster tool, the Python part of it is what's going to handle all the issuing of OpenStack resources. So first it'll check quota, then it'll make sure that the user doesn't already have in this cluster space, doesn't already have existing resources. If it does, it deletes them. Once it's got a clean slate, it deploys two heat stacks, one heat stack for instances, a second one for all the volumes, connects them all together in every iteration possible, and then prepares it for the Ansible playbooks to take over and start their implementation of whatever the user has defined ahead of time as the different configuration they want in their Spectrum Scale cluster. So, yeah, prior to running the tool, the user would have had to create that config file. User specifies how many nodes, as in how many VMs they want this cluster to have, the number of disks, the size of the disks, lots of different scale things that they can specify. If this cluster is supposed to go ahead and create a file system, have it mounted, which operating system they want on these nodes. We support several different flavors of Ubuntu, Red Hat, of course Red Hat SUSE, Red Hat 7, 8, and 9, and then which node architecture they want these nodes, bless you, and yes, architecture, that's where we finally get to the architecture part of the presentation. So in this OpenStack environment that we've got set up, we have machines of two different architectures to start with. Most of it is x86, but we have at least a quarter of them are power machines, or running power architecture. They're running PPC 64LE, and but there are other architectures that are supported by both the GPFS and OpenStack, AIX being one of them, or IX being another OS that'll run on those power machines if you paid IBM for the privilege. Z mainframes, it'll run both, and coming soon, I think OpenStack already works on ARM, I've read, but Spectrum Scale has not quite gotten that far along to have ARM provided. And so it turns out kind of like secret ingredient soup. There is no magic secret to running multiple architectures in OpenStack. They're as long as you've installed the correct packages on a power machine, it functions just like any other machine in an OpenStack cluster. You can create availability zones, and like I guess if sometimes you would split an availability zone off by geography, or you want machines that have a particular type of disk in them, you can just do the exact same thing with an architecture. And I shove all the power machines into their own availability zone, and they work great. It's yeah, it's great. Speaking of power, I had a I'll spare you guys the history lesson on the power architecture, but it is open sourced, and Power 10 is out now. I should hope to have one of those in the environment coming up soon. AIX being the other operating system mentioned in terms of being able to run on power machines, also released by IBM. And then, the talk promised also a kind of a bit of a breakdown of pluses and minuses, or gotchas that could lessons learned from running this guy for a while. There's loads of positive results for running multiple architectures, because what's more fun than geeking out and having more than one architecture in your environment. Negatives for this would be, there's no support, so you're on a roll your own basis if you're going to do this. Being IBM, you might think we could just go grab Rojas P from Red Hat and have them support our endeavors, but they only support x86. And users tend to want to lean towards x86. That's what they'll grab because they are familiar with it, even though they'll say that they can use power. They'll just kind of default to x86, which isn't necessarily a problem until you're trying to plan for capacity, because once you've if you go to the overview screen in your OpenStack environments, and your manager sees that there's 2 terabytes of RAM free, he says, hey, we've got plenty of room. And you say, no, all of those 2 terabytes are all in power machines, and everybody else is crammed into the x86 machines, and we're running out of space quickly. As for the cluster tool that I was describing, how we set users up and provide them a way to create GPFS clusters at any point in time, all day long, however they want to. This has had lots of positive feedback, especially some of the performance or deployment-driven users deploy different clusters with different OSs multiple times, every day, every week. And appreciate not having any manual steps at all. Of course, going back to that network diagram that I showed you, another positive is that since users log into that Bastion node, and all the VMs for any of these created clusters are all on private networks, corporate security scans never see any of them, and everybody's happy. Users don't have to register them. You don't have to take up any time or resources or cycles on those VMs trying to run antivirus software. Therefore, tests are a bit cleaner, and it just works out better. The network isolation provided by granting each user their own 3 networks works out well as well. It's plenty of overhead for Neutron, but just having 3 huge networks that you're trying to keep track of everybody's nodes on would lead to some network congestion, and everybody appreciates that not being the case, as is sometimes want in our bare metal environments there in the lab. A negative part of the way we've set this up is that some users you just can't reach. You give them this VM, it's small because we just intend them to log into it and run the commands to launch their clusters. We tell them, don't mess with it really, because I'm going to have to run antivirus software on it to keep it up to date, to keep it compliant with corporates. I may need to update the OS. I may need to, Ansible may change and I may have to install that, or I may have to completely swap out the VMs. the VM itself. 85% of users that say, okay, I'll leave it alone and use it just like you told me. And then there's the others that will, they say, oh, I need to use this as a dev machine. Oh, I need a build machine over here. And, once you can't just go in and have your way with it, it causes not necessarily headaches, but it's just not as streamlined as it could be if the tool wasn't reliant on being on its own VM. What is next for OpenStack? So Poughkeepsie usually gets shortened to poke, and you can wittily enough combine that with OpenStack to make OpenStack, not to be confused with DopenStack of ill-reported fame, or had its speedy demise. So anyway, the new environment Drake is already in flight as soon as I can get home and get back to work on it. Our old Frost environment is on hardware so old it still has IBM branding on it. So we have fresh hardware, a bunch of nice SR650s and 665s. We also ordered a new flash system 5000, which means we will no longer be using that kind of old, outdated GPFS driver. It'll no longer be a dog food environment, but we'll be using the Storewise fiber channel driver, which I've already tested out, and grease lightning, man. We also bought some new 100 gig switches, which I'm looking forward to the improved network, and we plan an ironic setup so that we can get, of course, bare metal installs of these clusters, but then we can stick NVMe drives in some of these hardware and get users testing with those, because at the moment we don't have any in the environment. And as I mentioned, I got some P10s coming. That'll keep me busy for a while. Just real quick, I got to throw out some love to the guys I work with, because I certainly didn't implement this all by myself. If I'm lucky, I did a fraction of it, most especially Christoph Kyle, who wrote the original cluster tool, and PC, who did the original architecture of the Frost environment. And with that, I got nervous and talked way too fast, and I'm done early. Thanks, y'all.